Hello, everyone, and welcome to the second episode of our series on quantum mechanics. In the previous video, we explored humanity's early understanding of light and discussed how Planck made a groundbreaking proposal while addressing the ultraviolet catastrophe. He suggested that, although electromagnetic waves seem continuous on a macroscopic scale, their energy is actually quantized at the microscopic level. This means it exists in the smallest, indivisible units, which he called quanta. Now let's dive into today's topic. When light strikes the surface of a metal, it ejects electrons from the material. These electrons create an electric current, generating electricity. This phenomenon is known as the photoelectric effect, and it has practical applications in many fields today. The photoelectric effect was first observed by Heinrich Hertz in 1886. But for nearly 2 decades, its mechanism remained a mystery. Why does light cause electrons to be ejected? In 1905, Albert Einstein provided an explanation in a groundbreaking paper. He proposed that light doesn't transfer energy as continuous waves, but as discrete packets of energy called light quanta, now known as photons. Let's explore this concept with a simple experiment. When we shine a flashlight on a metal surface, the pointer of an electroscope doesn't move, indicating no current is generated. Even increasing the intensity of the light doesn't change the result. But when we switch to higher frequency light, like ultraviolet light, the pointer moves, showing that a current is produced. This is the photoelectric effect in action. Einstein explained that a photon's energy depends on its frequency. Low-frequency light, such as infrared or visible light, doesn't have enough energy to eject electrons, so no current is produced. However, when the frequency exceeds a certain threshold, the photons have enough energy to overcome the metal's work function, W, and eject electrons. In other words, the photoelectric effect only occurs when the light's frequency is above a specific threshold. The intensity of the light doesn't determine whether the effect happens. It only affects the number of electrons ejected. Let's use a simple analogy to illustrate this. Imagine a low-frequency photon as a small person trying to lift a heavy object. They can't lift it because they don't have enough strength. Increasing the intensity of the light is like adding more small people. However, since light consists of discrete particles, these individuals can only work one at a time and cannot combine their efforts. In contrast, a high-frequency photon is like a tall and strong individual capable of lifting the heavy object alone. This is why even a weak beam of high-frequency light, such as ultraviolet light, can trigger the photoelectric effect. Einstein's hypothesis of light quanta not only explained the photoelectric effect, but also confirmed Max Planck's earlier quantum theory. This discovery laid the foundation for quantum mechanics. Interestingly, Einstein was awarded the Nobel Prize not for his theories of relativity, but for his explanation of the photoelectric effect, a breakthrough that transformed our understanding of light and energy. Have you ever wondered, is light a wave or a particle? By the 19th century, the wave theory of light was widely accepted by scientists. However, Einstein's explanation of the photoelectric effect revealed that light also behaves as a particle. So, what do waves look like as they travel? As shown in the image, when two wave sources vibrate in sync, they create interference patterns. In 1801, British scientist Thomas Young provided compelling evidence for light's wave nature through the famous double-slit experiment. In this setup, light passed through 2 narrow slits. If light were purely made of particles, you would only see 2 bright spots on the screen corresponding to the slits. But the actual result was far more fascinating, an interference pattern of alternating bright and dark fringes, something wave theory explained perfectly, while particle theory could not. Thomas Young's double-slit experiment conclusively demonstrated that light behaves as a wave. However, Planck and Einstein's theories irrefutably proved that light also exhibits particle-like properties. This duality left physicists in the early 20th century puzzled, is light a wave or a particle? Even Einstein expressed his frustration, famously remarking, "All the 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta?" Of course, today every rascal thinks he knows the answer, but he is deluding himself. Despite the challenges, scientists have made remarkable progress. Back in 1924, French physicist Louis de Broglie proposed his groundbreaking wave theory of matter, suggesting that everything, even you and me, has both wave and particle properties. A few years later, in 1927, American physicists Clinton Davison and Lester Germer, together with British physicist George Thomson, confirmed the wave-like behavior of electrons through different experiments. Around the same time, Danish physicist Niels Bohr introduced the principle of complementarity, explaining that microscopic particles, like photons, electrons, and protons, can behave as waves or particles depending on how we observe them. Today, wave-particle duality is not just a fascinating concept, but a cornerstone of quantum mechanics. You might wonder, how can something be both a wave and a particle? It's a fair question, especially since classical physics treats waves and particles as completely separate concepts, a perspective based on our everyday experiences. But nature follows different rules. Waves and particles aren't opposites. They're complementary. It's like a bilingual speaker. The language they use depends on the context, not because they switch languages, but because they adapt to the situation. Similarly, the wave and particle properties are inherent to matter itself, but under different conditions, they manifest in different ways. In 1935, Austrian physicist Erwin Schrödinger proposed a famous thought experiment known as Schrodinger's Cat. The experiment involves a closed box containing a cat, a bottle of poison, a piece of radioactive material, and a detection device. The radioactive material may decay within a given time frame, or it may not. If it decays, the detection device triggers the release of the poison, causing the cat to die. If it does not decay, the cat remains alive. The key point is that the decay of the radioactive material is a quantum event, and until observed, it is impossible to determine whether it has decayed. Quantum mechanics tells us that before observation, the material exists in a superposition of both decayed and undecayed states. Therefore, until the box is opened, the cat is in a superposition of both dead and alive. Only upon observation does the cat's state collapse into one of these two possibilities. Both dead and alive may sound absurd, but just like wave-particle duality, death and life in the microscopic world are not opposites or exclusions, but are in a complementary relationship. Although this goes against our everyday experience of the world, it is a fundamental aspect of nature. In 1961, German physicist Klaus Jungsen conducted an experiment involving electrons, mimicking Thomas Young's double-slit experiment. In this setup, electrons are ejected one at a time. If the electron behaves like a particle, it can only pass through one of the two slits, resulting in two distinct distribution areas on the screen. However, the surprising result was the appearance of clear interference patterns, a typical wave characteristic. This raised the question, how can electrons, which are particles, behave like waves and pass through both slits simultaneously? To investigate this, scientists used a device to observe the electrons. When the device was switched on, the electron behaved like a particle, forming two distinct patterns on the screen. But when the device was switched off, the interference pattern reappeared. This raises a puzzling question. Does the electron somehow know it's being observed? The significance of Jungsen's experiment was that it provided the first experimental verification of the superposition state at the level of individual particles, transforming a key concept of quantum mechanics from theory into fact. The idea of the superposition state had been proposed earlier, in 1926, when Schrödinger developed the wave equation to describe quantum systems, now known as the Schrödinger equation. This equation shows that the quantum state of a system can be represented by a wave function. Terms like Schrödinger equation and wave function might sound intimidating at first, but don't worry, we'll break them down for you. When an electron exhibits wave-like properties, it may be found in one location or another after being ejected. To determine the probability of its position, speed, or time of appearance, we use the wave function. In other words, the wave function is a mathematical tool that describes the superposition state of a quantum system and contains all the information about the system, such as the position, momentum, and energy of the particle. By calculating it, we can determine the probability distribution of the particle in different states or locations. Importantly, the wave function is not static. It changes with external influences such as time, particle interactions, light, temperature, observation, magnetic fields, or electric fields. The Schrödinger equation describes how the wave function evolves over time or space, much like how Newton's equations describe motion in classical mechanics. Many people assume that Schrödinger's famous cat thought experiment was meant to show that cats can exist in a superposition state. However, this was not his intent. Schrödinger originally devised the experiment to critique and satirize the Copenhagen interpretation of quantum mechanics. Developed by Niels Bohr and Werner Heisenberg in the 1920s, this interpretation suggests that matter exists in a superposition of multiple states until it is observed, at which point it collapses into a definite state, such as a particle or a wave. While the Copenhagen interpretation remains greatly influential in quantum physics today, Schrödinger found it absurd to extend these principles to the macroscopic world. But Schrödinger wasn't the only one to question this view. How does an electron know if it's being observed? What about challenges such as quantum entanglement, Bell's inequality, the EPR paradox, and decoherence? And could concepts like parallel universes offer alternative explanations? We'll explore these intriguing topics in the next episode.